All right, so here are V-belts. Basically, they have like a kind of a groove angle, okay? They kind of look like a V, and depending on, like, you have 3V, 5V, 8V, it depends on the size of this belt, okay? So this is what they would look like, the cross-sectional area, and they're commonly used, and you're going to be able to do an example on how to size one, okay? So let me go right here first. Here's that schematic, right, that I showed you in the previous video. And they've actually simplified and derived equations. So for a V-belt, the length of the belt is 2 times the center distance plus 1.57 times D2 plus D1, okay, plus D2 minus D1 squared over 4 times the center distance. Center distance is equal to B plus square root of B squared minus 32 D2 minus D1 squared all over 16, where B equals 4 times LP minus 6.28 times D2 plus D1. Theta 1 is 180 degrees minus 2 sine minus 1 of D2 minus D1 over 2 times center distance. Theta 2 is 180 degrees. I think I might have... Yep. Plus 2 sine to the minus 1 of D2 minus D1 over 2 CD. And then D becomes square root of CD squared minus D2 minus D1 over 2 squared. Okay. Now, I'm not going to show you how those were derived, but these are the fundamental equations you can use to figure out and size a V-belt. Okay. Let me fix this over here. Right. So those equations we're going to use. We're also going to use some charts. So here is figure 7.15, and this is for a V-belt, a 5V V-belt. Okay. So what we have here is the small sheave pitch diameter. So 1 over here. And then you have rated power. So each belt, the size, depending on the pitch diameter, will have a rated power. And this rated power, these lines on here, are for when you have a perfect 180 degree contact angle. Okay. Now sometimes you won't, depending on the exact sizes that you can buy. Okay. There's of these sheaves. Sometimes you get one that isn't going to make it 180 degrees. Okay, and I'll show you those corrections. But here you have RPM, 1750, 1160, 870. The solid line is when you have a velocity ratio of 1. Okay, so you can find those, remember, by the omegas or your pitch diameters. Okay, the dotted line is when you have a velocity ratio of the 3.38. All right, and so anything higher than that, it doesn't really change the rated power, and it gets kind of they don't work very well when you have a higher velocity ratio. Okay, so you can actually interpolate between which. So say your velocity ratio is 2, then you kind of go in between these two lines. All right, and we'll do an example to show you how to do that. All right, so rated power for pitch diameters and belt sizes. Okay, so a 3V and an 8V will have a different curves, and it depends on the RPM that you're rotating at. Down here, this is standard belt lengths, You'll find that LP might be, say, 162. Well, they don't make that, so you either go 160 or 170. All right, so that's table 7.2. And then here, these are corrections like I talked about if your angle of wrap is not 180 degrees. So you'd have to do a corrected power by multiplying this number by your rated power. Okay. And also over here, this is the belt length. If your belt length is not ideal, right, 1 would be ideal for these ones, then you'd have to correct. Okay, and these are, again, corrections based on values that were found in this chart. Because we use 180 degrees, that gives you the best contact, and anything more or less, you may have more contact or you may have less contact, so therefore you're going to reduce your power if you have less, right? So if you have less angle of wrap, you have less grip, you're going to have less power. And depending on the lengths, all right, sometimes if it's too long, you might have a little bit more power, okay? But if it's too short, right, it may be dragging on things and causing more friction. Okay, so this is just a quick example of, or idea of, a V-belt, equations that we're going to use in the next video to calculate how we do this. All right, thank you.